Well, first of all, thank you everyone for doing a bunch of different things and trying a bunch of different things. I think part of the reason we chose this particular problem was we wanted to pick a problem where you couldn't, there wasn't just one clear immediate right answer that was just download PPO and run it, which is true for a lot of different problems. So I think what would be good for us to discuss a bit would be, I think we can group the set of approaches people tried into maybe 4 different categories, and it might be fun for us to talk a little bit about why each category of approach worked better, because I think we could roughly speaking order these, even though there was differences in terms of implementation that led to slight differences, right? So I think what probably worked the worst, I think maybe one team actually tried this, was just throwing a policy gradient at the problem, right? Does anyone have any intuition for why this would work kind of poorly? Because if you think about it, right, all these fancy ChatGPT things are trained via PPO, right? So it's not complete nonsense. So there has to be a reason, right? Any guesses? Sparse reward is one thing, right? This is a very long horizon problem. There's something more basic though. Anybody? Yeah, go ahead.
Is this state space high dimensional?
Well, I mean, I would say the state space of language is much higher dimensional, right? I would argue that it really boils down to pre-training, right? Think about how for anything that looks like these large language models, right? You spend the vast majority of your compute just training on the entire internet, so you learn how to generate maybe not good text, but text in general, right? And then fine-tuning, as we'll learn kind of later in the course, is really doing mode selection on a small set of these things, right? So a lot of things like policy gradients are really, really bad at exploration. I don't know if Stephen covered this in this lecture, but to actually prove something like MPG converges the optimal policy, you need to assume your reset distribution covers the entire set of states the optimal policy visits. So that means almost by definition, this algorithm is really, really bad at exploration. So it turns out that for at least the domain of language models, the right answer there is just train on a bunch of data so you have a pretty good initialization, and then just poke the policy a bit. But if you're doing it from scratch, a policy gradient often is a really bad idea. The next sort of, I think, group of approaches we tried was variants on a theme of DQN, right? So beyond the fact that this was the, thing that was provided in the actual repo as a thing you could do, this worked better, right? But not as well as one might hope, right? Does anyone have any thoughts about why this worked better than policy gradients, but worse than the other things?
I mean, the approach, we do an epsilon gradient exploration, so that exploration factor is accounted in this. But since, let's say, if we are using grouped actions, we have 40 actions, so training that is slightly on the slower side. Therefore, if we use a critic network, the training is faster, but still, I mean, it didn't perform as well as the look-ahead approaches, as it didn't use the future tetrominoes in the queue.
So definitely future tetrominoes is definitely part of it, fully agreed. I would say another part is that exploration for this problem, even when you use the group action wrappers, is still kind of hard, right? As a general principle, all of you saw that if you ran this forever, you would eventually get good performance with EQN, right? But it's just actually doing that exploration of trying everything out, generally speaking, is very, very hard, right? Especially for extremely long horizon problems like this, right? You were running, some people are running these for weeks, it seems. The other thing I think I'd note there, right, is that a lot of the versions of DQN, right, actually tried to learn the policy directly from pixels, essentially, rather than using some sort of handcrafted set of features. I don't know if there's any sort of general wisdom about this. I think everyone in principle realizes doing things end to end should work better. But if you look at most let's say real world robotic systems, you often see them have sort of hand engineered features that were learned by somebody labeling things. I think the reason people are really excited about things like DLMs, foundation models, things like this, is that it turns out if you just have enough data, you can actually just learn pretty good general purpose features. But it turns out that when you try and do this for one particular task from scratch, it's often just much, much, much easier to just specify the features by hand, or label a data set with them and learn those, rather than try to get the whole thing to get backed out end to end. So I think it's a very specific thing to the problem. So then I think we had the things that looked vaguely like imitation, right? So these, I think that the obvious reason these were kind of annoying is because you have to collect the demonstrations, right? At some point, people get tired of playing Tetris unless you're a bit of an addict, right? But I thought there were maybe like two things that people mentioned that I thought were like, kind of interesting and kind of subtle. The first is that there were some times, right, when people were using, I forget which team was using like a computational expert, right? There was like some like program, right? And then your like policy or like in our game, you couldn't execute some of the same moves, like you couldn't do the T-spin or whatever, right? So a kind of problem that repeatedly shows up in imitation learning, and we'll talk about much more later in this course, is how do you deal with like sort of an unrealizable expert or an expert where you can't perfectly imitate them, right? This happens very, very frequently in practice when your expert is something like a human, right? And maybe your robot has a different set of perception systems, something like this, or it just like doesn't have some capabilities, right? Like my favorite example of this is like when you're driving an intersection, like if the person across from you does a hand gesture, you know what that means, but it's very weird for your car to be able to recognize the hand gestures of the other person if you're trying to like train an AV. The other thing I think that was kind of interesting, somebody brought up this point about how like when you like did the thing where you just like dropped the block all the way to the bottom, right? You couldn't correct anymore, right? I think we'll talk about more is that like for kind of things that look like imitation to work well, you basically can't have this sort of problem where you're kind of irrecoverable, right? Like when you're walking along a cliff, after you fall off the cliff, there's only one action to do, like as Drew put it, right? So that sort of recoverability kind of thing dictates a lot of how well imitation flavored approaches actually work in practice. Then there was the kind of the thing that seemed to work the best. There's some blog post that I think like 3 or 4, I don't know if it was the same blog post, but it seems like there's a pretty good blog post. But like this sort of like, some people call it heuristic search. I would call it something that looks like model predictive control, something that looks like this, right? So there were a few points there I thought that were kind of interesting. So the first, maybe the thing I wanted to make clear is, let's say we have that function we're taking the argmax over, right? To like pick where we're gonna like put the block, right? Let's think of just like the step one for a second. What is that function? Like, what does that function have to be for this to actually work? Yeah.
A Q value.
It has to in some sense be a Q value, right? Maybe it's not Q star, but despite the fact that people thought they weren't doing something from the course, you actually were. It really is a Q function in some sense, right? It's just that rather than learning it via like Bellman residual minimization, the sort of thing we talked about in the class, another way you can do it is you just perturb the weights of your Q function until it does the thing you want it to do. Right? So that was what the cross entropy method you all talked about is, right? Generally speaking, you should think of things that look like reinforcement learning and the cross entropy method as being part of a larger set of things I would call like just 0th order optimization, where rather than taking gradients, you essentially have samples of something and use that to update your parameters in some sense. So that was, I think, just a thing to mention. I think there was maybe like 2 other things that were kind of interesting. I forget which group did it, but somebody did an ablation where they looked at the number of steps of look ahead they did, right? And I think that is a thing I think we'll talk about more in like 2 lectures, but I think it's a really interesting question in some sense, why it's easier sometimes to learn to search rather than directly get the policy, right? Like in some sense, the fact that I did this 2 steps of look ahead and that worked better than me just trying to directly learn a policy, broadly speaking, is a very interesting thing, I think. We'll talk about, there's actually a really like clean theoretical explanation for why this should be true. I think that'll be in 2 lectures. The other thing I think is kind of cool here is that, have you guys heard of things like AlphaGo, AlphaZero, things like this, right? They work fairly similar to the sort of systems that work the best out of the set of things we talked about here, where they're doing look-ahead search, test time planning, MPC. All these things are algorithmically speaking the same thing. There's one critical difference though. Does anyone know what it is off the top of their head?
It's a 2-player game. But here the environment is deterministic. But in a actual AlphaGo environment, we don't know the exact next state because we need to simulate the other player as well to get the next state. But here we didn't have to do that.
Right. So you can do things like AlphaGo, and they do it for one of the papers on like just not even games, but general reinforcement learning environments. You can do the same thing there, but there's still like a more fundamental difference. Yeah.
So they take both the policy and the value functions into account when they rank the possible outcomes.
Yeah, so there's this sort of like thing that I think people try to do one version of this, but like there's almost a sense of like we talk about like policy iteration in some sense, right? There's almost like a version of like a dual policy iteration you can do, where essentially you take your current policy, you sample like the best things from it, and then you pick the best of those samples and you use that to update your policy, kind of as a kind of like a dagger style or interactive imitation style approach. And that is kind of fundamentally how I would say like things like AlphaZero or AlphaGo are actually like trained. Um, so I would say that like for a game of the complexity of Tetris, just like fixing a function and then just optimizing it seems to be good enough. But as you get to harder and harder and more complicated problems, you often want to update that function adaptively based on what you've actually seen. So like I think that that is a really beautiful and interesting thing we'll talk about more, I think, in a few lectures. The last thing I thought was kind of cool is a few different people tried like learning the weights rather than actually in a variety of ways, rather than like just like using the ones from the blog post, right? You know, one way or another, someone had to learn those weights, right? So that's still like a hard problem, I would say. I think that the stuff we'll talk about in the imitation learning section of this course is a lot about how you actually learn those weights. It turns out that like here there was like an underlying reward function. So one way or another, you can kind of boil this down to a relatively simple optimization problem. But for a lot of like real world systems, it's much, much harder to actually say what you want. And therefore like learning the weights or learning those cost functions kind of ends up becoming the central problem. So I think about something like driving. I don't know how to write down a function that captures what good driving is. Same thing for language models. I don't know how to kind of capture exactly what good language is in some sense. So what we'll sort of be talking about for the imitation and RLHF parts of the rest of the course are really like how you actually learn the specification from data in some sense. But yeah, thank you everyone. It was really cool seeing the diversity of solutions.
You want to say something about the winner gets some prize from you or Drew, and also you'll be designing a homework too.
I am? Okay, so turns out you guys now have an extra homework. Yeah, I think prize TBD. We have some thoughts. We're still thinking it through. In terms of the like homework, yes, at some point there will be a homework of some sort. One more sort of like just like more theory homework. We're not going to make you guys do another class competition. Originally, we were a bit optimistic on that part, I think. And then, yeah, I think we'll probably switch.
And then there's the project.
We'll switch more to like, project proposals, and actually doing the project stuff after this. But yeah, I hope if nothing else, you kind of got a little bit about how, you got to spend a little bit of time thinking about how you actually take some of this theory and some of these ideas and actually scale them to practice. I feel like oftentimes the things that actually influence practice are not what you expect. But I think there's still a lot of intrinsic value in just knowing the space of approaches from theory and algorithms. But yeah, I think I'm over time. But yeah, thanks guys.